All right, we're going to do a little screencast here about what causes electromagnetic waves. How are they generated? So if you did some reading in chapter 25, you probably saw that the thing that causes an electromagnetic wave, that produces an electromagnetic wave, is an accelerated charge. The key here is accelerated. Okay, it's not just a moving charge, and I'm going to write that down for emphasis because we talked a lot about in previous chapters how a moving charge will create a B field. Well, that's true, but an accelerated charge will create an electromagnetic wave. So that's the genesis of the whole thing, is the accelerated charge. We know that a changing electric field can produce a changing magnetic field, but we know that a changing magnetic field then also produces a changing electric field, and it goes on and on and on. So it's a feedback loop. Basically, you've got this electric field producing a magnetic field that produces an electric field that produces a magnetic field. So it's kind of shown here in this graphic from your textbook, and it shows that a changing B field, so this is where it's starting with this B field. For whatever reason that it's changing, it produces this changing electric field. And it's just exactly like we learned it before. So if the B field is changing in this direction here, let's say this was the north pole and that's the south pole of a magnet, if it's changing in that direction, then the electric field that's produced will be in a direction that it creates an E field or a current. If you want to think of the E field as a current, previously we were thinking about a moving charge. Now we're thinking about an E field. To produce the direction of the E field will oppose the B field that created it in the first place. So you can use that right-hand curl rule to try and predict which direction that E field is going to go, just the same as we did previously in the electromagnetic chapter. So then you've got this changing E field that produces a changing B field over here that produces its own changing E field, and it just continues to go on. Obviously weaker intensity as you go further out the chain. So that's kind of the genesis of the electromagnetic wave and how it gets started. Antennas can be used to start electromagnetic waves. So think about radio waves that are produced by radio antennas. This diagram shows an alternating EMF source. So that would be like AC current. So the EMF, the potential changes from positive to negative. Let's say if this side is positive and this side is negative, at one instant in time, then a second later, this could be positive and this could be negative. So it's changing the direction of the potential difference, which changes the direction of the current in the wires. So here are the antenna elements. Over here, you have to have two different elements, obviously. Here's how you would actually produce an electromagnetic wave from that antenna. So they're calling it a They're calling it a dipole antenna because obviously one end is positive, one end is negative, but it's changing because it's alternating current. So you see the E field, positive charges on this end because at this instant in time, at time zero, current's flowing this way from the negative to the positive side here. So you've got negative side of the antenna here, the positive side of the antenna down here. So if you remember, E fields point from positive to negative, so the E field is in that direction. And a changing B field is created that's in a perpendicular plane to the E field. So if the E field is vertical, the perpendicular plane horizontal would be the B field. And then that's going to change as time goes by because you got to keep in mind that the source that's hooked up to this, the EMF source, is changing from positive to negative. So this is increasingly positive as you go from this first case or first figure to the second figure. So I've got even more positive charge here on this in the second figure. So I've got a stronger E field, a larger E field vector here in figure 2. Now it's actually starting to switch direction. So this is at its max condition here of polarity, where you've got maximum positive and negative separation on this antenna. Now the EMF source here changes sides. So now the alternating current is flowing this way. So I've got some of that positive charge being reduced from 4 down to 2. So my E field vector gets short. Again, here I've got an equal number of charged particles on both ends of that antenna, so there's no vector here. So if you think about it, I've gone from a kind of a short E field vector pointed up, large E field vector pointed up, small E field vector to none. Kind of looks like this. I'm down in the bottom here in this picture. Here's my short E field vector. A second later I've got a longer one. Second later I've got a short one. Back to 0, which is this condition right here. And then it goes in the opposite direction. Short, longer, short again, 0. So if I trace that with my green pen right there, you see the shape of that electromagnetic wave, just like that. And notice how the B field that's changing is in the plane coming in and out of the page. So here it's coming out of the page long, out of the page, or this is no B field, into the page, maximum into the page, coming back towards me, but into the page still. Here it is 0, coming out of the page, and then maximum out of the page. So when you put those two things together, you get something that looks like this. We've got that E field in a vertical plane, which is a sine wave, and then you've got the B field, which is in the horizontal plane, in and out of the page, which is also a sine wave. You see they're in phase, but they're in a perpendicular plane to each other. So that's a depiction of an electromagnetic wave. The entire electromagnetic spectrum, as you saw in the AP Physics 2 College Board presentation, consists of radio waves all the way to gamma waves, and the light spectrum is right in the middle. So we can only see a certain portion of the electromagnetic spectrum, but all of the waves are represented like this, and it's electromagnetic because there's an electrical field component and there's a magnetic field component to it. So I hope that makes sense and explains a little bit about what causes an electromagnetic wave, and this combined with that College Board review video should give you a good grounding on electromagnetic waves and the electromagnetic spectrum. Okay, stay safe, stay close to home. Take care.